Hello everyone, Christina here. Welcome to the second part of API Monitoring Deep Dive. In the previous episode, we showed how we started this exercise following some questions we received from our Udemy students. So we discovered during our analysis that there is an interesting behavior that can affect API Monitor tool if we're using the low-level instructions to load functions dynamically. With this in mind, this episode will contain quite a bit of assembly code. Please pause the video when needed and check the code yourself. Even try it out. Remember that practice is key here. In the previous episode, we saw that a strange line of code was causing API monitoring to crash. In API Monitor tool, we have a few ways to attach to programs. For this scenario, actually all modes are affected. Let's run the sample and see how. Let's see the first couple of them. We'll actually have the same behavior with all the other types of attachments. All of them cause the program to crash. Let's understand what's happening. A quick reminder: getProcAddress is a function exported from kernel32.dll which allows us to resolve functions dynamically. It is very popular for Metasploit shellcode, and it's handy because it allows one to hide names of function being imported. They will be hidden from static analysis and only visible during dynamic analysis. So what we're trying to do here is call this function in a different way, jumping past the first 2 bytes of the function. We've talked in the previous video about their role and why we can skip them. We push 2 parameters to the function on the stack in reverse order. First is the handle to the DLL that contains the function to resolve, and the second one is a pointer to a function name. It is not important what function is resolving. It just matters that it will trigger a crash. So here we want to resolve, let's say, function internet open. Push its name on the stack, and then here, instead of calling getProcAddress itself, we call its third byte. A side effect of this call instruction is that it adds the next code address on the stack, this one over here, and then jumps to this label, which further jumps past the header of getProcAddress, as we said. After finishing, it will clean the stack and return to the saved address, this one over here. This move instructions saves the returned offset into a local variable and then continues the execution. This code works fine if we execute the application normally. See here that we get the fake net binary served from this URL. The code behaves as expected. When we tried it before inside API Monitor, it crashed because probably it relies on the function header to do the hooking. So this first trick completely blocks API monitoring interceptions. The second one uses a bit more shellcode, this block over here, to resolve the address of getProcAddress. At the end of the code, which we'll explain in a moment, we will have that address saved in a local variable. This is very important because having this address will allow us to resolve dynamically any function in a very stealthy way. If we would rely on calling getProcAddress as usual, API monitor would be able to intercept the calls. In our case, we'll resolve its address manually. See all the functions resolutions below. This is the one in this code. Let's rebuild the solution. Before that, we will comment the code that triggers the crash. Then start by monitoring a new process. The application runs as expected, but there are not very many API calls from it. There is only this internet open call. All the other function calls are hidden. Internet open is being resolved differently over here, remember, via this small piece of assembly shellcode. Now let's go through the big block of code and explain what's happening. We'll go block by block because there are a lot of instructions. The first part just allocates space on the stack. Next, we push the name of a function we want to resolve, in this case getProcAddress, in reverse order in 4 bytes chunks. Next, we obtain the address of kernel32 library, starting from the PE header and going to the list of modules. Next, we go past the PE header and we reach the export table. The export table contains the names of all the functions exported by the library, their RVAs and their ordinals. Next, we loop through all the function names and find the one that we're interested in. This is the loop. For each function, we'll compare its name with the name we stored on the stack. Here is the comparison in assembly code. If a function is found, we then return its virtual address in EAX register. At the end of the shellcode, we need to make sure to clear the stack by clearing the local variables and whatever we pushed on the stack ourselves to return the program to the same state. Finally, at the end of the shellcode, we save the address we found for the function into a local variable. Remember this local variable, whose name ends with 2, will actually have the address of getProcAddress function and will be used to dynamically resolve additional functions like all these ones below: Internet Open URL, Internet Close Handle, and Internet Read File. As a result of this, all these functions resolved dynamically will be hidden from API Monitor. Remember that Internet Open URL and the others were not present in the listing. The only function correctly intercepted by API Monitor was Internet Open, which was resolved differently and could have easily been hidden also. That's the code over here. I know it is a lot of assembly, but bear with me. If you're curious to understand the shellcode better, study it by yourself. To recap, this whole big block of code over here resolves simply the address of a function in a way that doesn't rely on the automatic imports. It will go read the PE header of the main module, find exports tables, then find the function address manually. A very similar trick is used in shellcode generated by Metasploit framework. Dynamic function resolution from Metasploit, download exec shellcode are also completely hidden. Make sure to practice with this one and see if you can test it on your own. Thank you very much for watching. Cheers!